Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structural analysis, truss analysis, method of joints. Before discussing about the methods for analysis of truss, let us know about trusses. A truss is an engineering structure that is made entirely of two force members. In addition, statically determinate trusses that can be analyzed completely using the equilibrium equations, must be independently rigid. This means that if the truss was separated from its connection points, no one part would be able to move independently with respect to the rest of the truss. Trusses can be broken down further into plane trusses and space trusses. A plane truss is a truss where all members lie in a single plane. This means that plane trusses can essentially be treated as two-dimensional systems. Space trusses, on the other hand, have members that are not limited to a single plane. This means that space trusses need to be analyzed as a three-dimensional system. Analyzing trusses. When we talk about analyzing a truss, we are usually looking to identify not only the external forces acting on the truss structure, but also the forces acting on each member internally in the truss. Because each member of the truss is a two-force member, we simply need to identify the magnitude of the force on each member, and determine if each member is in tension or compression. To determine these unknowns, we have two methods available: the method of joints, and the method of sections. Both will give the same results, but each through a different process. The method of joints focuses on the joints, or the connection points where the members come together. We assume we have a pin at each of these points that we model as a particle. We draw out the free body diagram for each pin, and then write out the equilibrium equations for each pin. This will result in a large number of equilibrium equations that we can use to solve for a large number of unknown forces. The method of sections involves pretending to split the truss into two or more different sections and then analyzing each section as a separate extended body in equilibrium. In this method we determine the appropriate sections, draw free body diagrams for each section, and then write out the equilibrium equations for each section. The method of joints is usually the easiest and fastest method for solving for all the unknown forces in a truss. The method of sections, on the other hand, is better suited to targeting and solving for the forces in just a few members without having to solve for all the unknowns. In addition, these methods can be combined if needed to best suit the goals of the problem solver. Here, in this video we will discuss about the method of joints. The method of joints. The method of joints is a process used to solve for the unknown forces acting on members of a truss. The method centers on the joints or connection points between the members, and it is usually the fastest and easiest way to solve for all the unknown forces in a truss structure. Using the method of joints. The process used in the method of joints is outlined below. Step 1. In the beginning, it is usually useful to label the members and the joints in your truss. This will help you keep everything organized and consistent in later analysis. In this video, the members will be labeled with letters and the joints will be labeled with numbers. Step 2. Treating the entire truss structure as a rigid body. Draw a free body diagram, write out the equilibrium equations, and solve for the external reacting forces acting on the truss structure. This analysis should not differ from the analysis of a single rigid body. Step 3. Assume there is a pin or some other small amount of material at each of the connection points between the members. Next, you will draw a free body diagram for each connection point. Remember to include any external reaction or load forces that may be acting at that joint. A normal force for each two-force member connected to that joint. Remember that for a two-force member, the force will be acting along the line between the two connection points on the member. We will also need to guess if it will be a tensile or a compressive force. An incorrect guess now, though, will simply lead to a negative solution later on. A common strategy then is to assume all forces are tensile, then later in the solution any positive forces will be tensile forces and any negative forces will be compressive forces. Label each force in the diagram. Include any known magnitudes and directions and provide variable names for each unknown. Step 4. Write out the equilibrium equations for each of the joints. You should treat the joints as particles, so there will be force equations but no moment equations. With either 2, for 2D problems, or 3, for 3D problems, equations for each joint. This should give you a large number of equations. In planar trusses, the sum of the forces in the x direction will be 0 and the sum of the forces in the y direction will be 0 for each of the joints. Summation F equals 0. Summation Fx equals 0. Summation Phi equals 0. In space trusses, the sum of the forces in the x direction will be 0, the sum of the forces in the y direction will be 0, and the sum of forces in the z direction will be 0 for each of the joints. Summation F equals 0. Summation Fx equals 0, summation. Phi equals 0, summation. Fz equals 0. Step 5. Finally, solve the equilibrium equations for the unknowns. You can do this algebraically, solving for one variable at a time, or you can use matrix equations to solve for everything at once. If you assumed that all forces were tensile earlier, remember that negative answers indicate compressive forces in the members. Analysis of the statically determinate trusses using the method of joints. What is statically determinate truss? How do we analyze them? Truss structure is an interconnected network of slender members, each capable of carrying an axial force only. The forces is either compressive or tensile force. Theoretically speaking, no shear force or bending moment is present in truss members. Several truss configurations usually seen in building roofs and bridges. Pratt truss. This is one of the most popular steel roof truss types, and it is quite economical. This particular type of truss offers some interesting features, mainly thanks to the fact that the vertical members provide tension, while the diagonal ones are bringing in compression. It's important to note that these trusses can be used for spans that range between 6 to 10 meter. Advantages of Pratt truss. Aware of members' behavior. Diagonal members are in tension, vertical members in compression. The above can be used to design a cost-effective structure. Simple design. Well accepted and used design. Disadvantage of Pratt truss. Not as advantageous if the load is not vertical. Best used for where a cost-effective design is required, where a mix of loads are applied, where a simple structure is required. How truss. This type of truss is a combination of steel and wood, which makes it elegant, while also offering a very appealing design. Almost everything is made out of wood, however, the tension members or the vertical members are manufactured out of steel in order to offer extra support and reliability. One thing that makes the Howe truss extraordinary is the fact that it has a very wide span, as it can cover anything from 6 to 30 meter. This makes it versatile and very useful for a wide range of project types. K-truss. The K-truss is a slightly more complicated version of the Pratt truss. Its main difference is that the vertical members have become shortened, improving its resistance against buckling. It does, however, have similar pros and cons to the Pratt truss, and although it is not widely used, it is a strong design. One of its main disadvantages is that the members don't always behave as expected. A member may be in compression under one load scenario and in tension under another. Warren truss. A Warren truss or equilateral truss is a type of engineering truss employing a weight-saving design based upon equilateral triangles. The Warren truss consists of longitudinal members joined only by angled cross members, forming alternately inverted equilateral triangle-shaped spaces along its length. Generally, we assume truss members are connected to each other using frictionless pins. This means, if we have two truss members that are joined together, one is free to rotate relative to each other. In other words, truss joint cannot resist any bending moment. Since neither the joints nor the members of a truss are designed to carry any bending moment, applied load needs to be placed at the joints. No load should be applied directly to a truss member. Here is a simple truss structure with 5 members. The frictionless joints are labeled as A, B, C and D. The truss is subjected to a horizontal force of 5 Newton at joint C, as shown in below figure. The entire structure rests on a pin support at band A, roller support at A. The truss is said to be statically determinate if its member force can be calculated solely using the equilibrium equation. If number of unknown forces equals number of equilibrium equation, then truss is statically determinate. So, how many equilibrium equation can be written for a truss structure? Total number of equilibrium equation is equal to 2 times the number of truss joints in the structure. Total number of equilibrium equation equals 2 number of truss joint. If the truss has 4 joints, we can write 8 equilibrium equations for it. For this example, number of equations equals 2 times 4 equals 8. Why 2 times the number of joints? Now let us accept it as a fact this time. We will answer this in a minute. What about the number of unknown forces? How many of them do we have? Number of unknown forces equals number of truss members plus numbers of support reaction. Here, the truss is having 5 members. Each member carries an axial force, which needs to be determined. Here, the truss is having 5 members and 3 reactions. Further, the structure rests on a pin and a roller support. There are 3 unknown reactions. The pin supports provide 2 reactions forces and the roller support has 1 reaction force. Therefore the total number of unknowns is 5 plus 3 equals 8. Number of unknown forces, 5 plus 3 equals 8 here. Number of unknowns equals number of equations. Number of equations equals 2 times 4 equals 8. Number of unknown forces, 5 plus 3 equals 8. Therefore, the truss is said to be statically determinate. How do we analyze such a truss? How do we calculate the member forces? There are several truss analysis techniques. Here we are going to explain and illustrate a technique called the method of joints. This technique is a direct application of the principle of static equilibrium. According to this principle, if the structure is in equilibrium, then not only the equilibrium equations must be satisfied for the structure as a whole, but they also must satisfied for any of its part. For example, suppose we have a simply supported beam with 3 support reactions, as shown in figure. We conceptually cut a beam into 3 segments, with the correct internal forces shown at the cut points. Then the equilibrium equation must also be satisfied for each segment. Summation Fx equals 0 summation phi equals 0 summation m equals 0 if the entire structure is to remain in equilibrium. We can apply this basic principle to analyze. Here is our simple truss. Drawing the free body diagram of the above truss. Keep in mind that each truss member carries an axial force only. Let us refer to the axial force in member AC as F. AC. Similarly, let us call the force in member BC. We labeled each forces of the remaining members. F. AC equals force in member AC, F. BC equals force in member BC, F. CD equals force in member CD, F. AD equals force in member AD, F. BD equals force in member BD. Now, let us separate the members from the joints, that is, we divide the entire structure into 9 segments. There are 5 member segments and 4 joints segment. Let us see a segment containing member AC. As the member carries axial force, but we do not know the magnitude of the force. We also do not know the force is compressive or tensile. Since we have to draw a free body diagram, we need to assume the direction for the force. Let us assume the member carries a tensile force, so the free body diagram for the segment looks like. Free body diagram for AC, see figure. Similarly for the other members of the truss. The only force present in this diagram is the unknown tensile force, which we have labeled F. AC. Free body diagram for other members as shown in the figure above. F BC F CD F AD F BD, where each member is assumed to carry an unknown tensile force. Now, let us draw the free body diagram for the joint segments. Now let us examine the joint A. It connects member AC and AD. Since member AC is attached to the joint, the axial force and the member also acts on the joint. We show this by placing AA on the joint node. Note how this joint force acts in the opposite direction to the same force acting on member AC. This is the case because the two forces must cancel each other out. That is, if we reconnect member ACTO joint A, the sum of the internal forces must vanish. This could happen only if the two forces acts in the opposite direction, so they would add up to 0. There is one more member force acting on the joint, the force in member AD. Again, we place this force at A in the opposite direction to the force shown on member AD. This completes the free body diagram of joint A. At the joint B, there are two member forces, the force in the member B and the force in member BD. At the joint C, there are three member force acting on it, fork member, the force in member B and the force in member CD. At joint D, there are three members forces, F, ADF, B and F, CD. Now, we have the complete free body diagram for each member and joint for an entire truss to be in equilibrium. Each truss member must be in equilibrium and each joint must be in equilibrium. Here, we can see that the equilibrium equations are satisfied. For each member, the two force vectors shown in each member cancel each other, that is, their sum equals to 0. And since there is no bending moment or shear force acting on the member, the moment equilibrium equation is automatically satisfied. Now, let us see the joint segment. Each joint has to be in equilibrium. This means, given the free body diagram of the joint, sum of the forces in x direction must be 0. Sum of the forces in y direction and sum of the moments about the joints must be 0. Summation Fx equals 0, summation phi equals 0, summation m equals 0. Note that the moment equation is automatically satisfied since all the forces passed through the joint. Therefore, we only need to examine first two equations. We will solve this example in next video. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.